In this lesson, we're going to talk about measures of dispersion. Starts off here, to order food at McDonald's restaurant, one must choose from multiple lines, while at Wendy's, one enters a single line. The following data represents the wait time in minutes in line for a simple random sample of 30 customers at each restaurant during the lunch hour. This data is available on StatCrunch. You will just search Wendy's versus McDonald's, and you can open it up. So for each sample, answer the following. What is the mean wait time? So I'm going to go into StatCrunch, and again, it's under data sets. You can search it. I opened it up. We want the mean wait time for each, and this is a sample. So we're going to go to Stat, Summary Stat, Columns. I went for Wendy's and McDonald's. When you guys are selecting more than one, you just hold down the Control button. If you're on a PC or a Chromebook, if you're on a Mac, you hit the Command button and select. So let's see here. I don't want all of these. I might look at that. Alright, let's just do this for now. And compute. So we can see for Wendy's, the mean wait time is 1.391 minutes, and McDonald's is 1.389 minutes. So McDonald's was 1.389 minutes. Wendy's was 1.391 minutes. Okay, so part B, draw a histogram of each restaurant's wait time. So did this in StatCrunch. I just went ahead and threw it on here, but I will show you. We're going to go to Graph, Histogram. I don't know if I can do both at the same time or not. Frequency. Let's see if it does. It does. Okay, go back and forth. So here we have Wendy's with the frequency and McDonald's with its frequency. So we can see those two different histograms, and I have them on mine here. So talking about these histograms, notice that for McDonald's, our wait time axis goes from 0 to 5. For Wendy's, our wait time goes from 0 to 4. So up to 4 minutes was the longest time waited, versus up to 5 minutes was the longest time waited for McDonald's. So if you look at the shape of the graphs, it looks like McDonald's, we got some skewed right data here. And for Wendy's, it's a little bit more bell-shaped. All right, it's not as skewed to the right. So we'll go a little bit more bell-shaped. All right, so for McDonald's, our horizontal spread, it's spread out over all possible values. Whereas the majority of our data for Wendy's, our horizontal spread is that clump of the bell. So that's representing the horizontal spread. All right, so which restaurant's wait time appears more dispersed, and which line would you prefer to wait in? Well, since McDonald's has more horizontal spread, it is more dispersed. This would be McDonald's. Which line would you prefer to wait in, and why? So, let's type this one again. Okay, we would prefer to wait in Wendy's line because there is less horizontal spread and the wait time is more consistent. All right, so because there's less horizontal spread, that means you have more consistency in the wait line. So if you're choosing Wendy's, you're more likely to wait among that smaller amount of time, whereas McDonald's, you don't have as high likely of a chance of being in one, being there for the smaller amount of time. Okay, so that's what we're talking about. It's kind of how spread out our data is. So here we're going to find the range. The range is represented with a capital R. It's just the difference between the largest and the smallest value. So to find the range, you just take the max value minus the minimum value. So from our travel time to work for that startup web development company, find the range. Well, our range is going to equal the largest travel time, which was 43 minutes, minus the smallest, which was 5. So our data values have a range of 38 minutes. All right, so second objective here is standard deviation. So we have population standard deviation and we also have sample standard deviation. So population standard deviation is this formula here. We're going to talk about what all that means. And it's represented by this Greek letter sigma, okay? So I kind of draw an O with a tail on the right-hand side of it there. So the formula, what we are doing here is we are going to take each data value and subtract the mean and square it. And then we're going to add all of those together. So it's the sum of each data value minus the mean squared. And then we're dividing by capital N. Remember, capital N represents the number in the entire population. And then we're going to take the square root of that. So we're going to find the sum of each data value minus the mean, square it. Or we're going to take each data value minus the mean, square it, find the sum of all those, divide by the number of population, and then take the square root. So when we are doing this by hand, it's going to be helpful to set up a table to help us out. So the following data represents the travel times that we had. Compute the population standard deviation. Okay, so we have our data values, which are 23, 36, 23, 18, 5, 26, and 43. All right, well, the next part that we are going to do is we are going to take each data value and subtract the mean. Well, in order to do that, we need to know what the mean is, which we found in a previous lesson. All right, so we know that capital N is 7, our population size. We found before our mean is 24.86 minutes. Okay, so for this part of our formula, we're going to take 23 and subtract the mean, which was 24.86. That would give us negative 1.86. And we'll take 36 minus the mean, which would be 11.14. We're going to take 23 again, which we already did, which is negative 1.86. We're going to continue this. All right, so 18 minus the mean would be negative 6.86. 5 minus the mean would be negative 19.86. 26 minus the mean would be 1.14. And 43 minus the mean would be 18.14. Okay, so from the formula we have done just this part. So now next thing we're going to do is square that. So we're going to take those values we just got and square them. Alright, so doing that, we're taking negative 1.86 squared, which is 3.45. Then we're taking 11.14 squared, which is 124.16. We've already done this one, which is 3.45, but we are going to continue this. We're taking each of those and squaring them. All of our values will be positive. So we got 47.02, 394.31, 1.31, and 329.16. So now we have done this part of the formula. Next, we're going to find the sum of all of those. So we need to add all of those together. So at the bottom here, I'm just going to do the sum of that. You add all those together. You get 902.86. So now what's left to do is divide by the number in the population. So sigma is equal to the square root of 902.86 divided by 7. And that gives us a value of 11.36 minutes. So that is our population standard deviation. Let's see if we're gonna do that. No. All right, so if I'm showing you this in StatCrunch, I know I don't have, I'll go ahead and type those numbers in real quick. Let's see, we got 2336. Uh, 2318. 526. And 43. Okay, so if I'm doing my summary stats for that I just typed in, and let's do, if I just do that standard deviation right there, because it says standard deviation, I'm going to compute it. It tells me my standard deviation is 12.266874, which is not what we just got. So what's happening is they think that that data set is a sample. Well, the sample standard deviation uses a slightly different formula. So what we are going to do is, instead of selecting this standard deviation, we're going to go down here to the unadjusted standard deviation, compute, and that would be 11.36, which is what we got. So the unadjusted means we are taking it of the population. Nothing has been, we're just dividing by the number in the entire population. All right. So I'm going to put select unadjusted standard deviation for population. Okay, so here in our sample standard deviation, we represent sample standard deviation with the letter S, lowercase s. So here's your formula. Essentially, really the same. You're taking each data value minus x bar, which is the sample mean, and squaring it for all of your data values, and then you're adding them together. This time you're dividing by n minus 1. So that's the number in the sample minus 1, and then you take the square root. But n minus 1 is referred to as the degrees of freedom. If you study statistics more, you'll learn about it more, but really it's just making, it just helps this equation become more accurate. So that's what it is, and that's how you use it here. So example 3, computing a sample standard deviation. Here are the results of a random sample taken from the travel times for all 7 of those employees. So find the sample standard deviation. Okay, well, to do this, very similar, we're going to make a table. But the first thing we need to know is what is the sample mean? So x bar would be 5 plus 26 plus 36 divided by 3, which is 22.3 repeating. So now we can make our table. So we're going to have our individual data values, which are 5, 26, and 36. And then we will take each data point minus the sample mean. So we're going to take each data point, minus the sample mean. So here we're going to take 5 minus 22.3333 and so on. Alright, so when we do that, we get negative 17.3333. We're going to take 26 minus 22.3333, which is 3.6667. And then 36 minus the sample mean is 13.6667. So now we need to square those. So we're going to take what we just got and square it. So if we do that, we have 300.443288. 89. If we take 3.6 repeating squared, we get 13.4446. And last, squaring 13.6 repeating 186.77868889. Okay, I'm just waiting to round to the end to get my most accurate answer here. So next we would find the sum of that column. So if we add all those together, that's 500.6 repeating. All right. So the last thing we do then is we find the sample standard deviation by taking the square root of that number And then dividing by the number in the sample, which is 3 minus 1. So we get a sample standard deviation of 15.82 minutes. All right. So if we were doing that one in StatCrunch, we would just choose the standard deviation, not the unadjusted standard deviation. All right. Example 4 here, we're going to compare standard deviations and talk about the meaning of them. So determine the standard deviation waiting time for Wendy's and McDonald's, which is larger and why. All right. So I still have my chart pulled up, so I'm going to edit. And I'm going to choose my standard deviation. Now, this was of a sample, so I'm good just choosing standard deviation. So the standard deviation for Wendy's is 0.7384, and for McDonald's is 1.2649. And that was of a sample, so that would be S. So this standard deviation for McDonald's, 1.2649. Standard deviation for Wendy's was 0.7384. All right, so we already knew that McDonald's had more horizontal spread. It was more dispersed. And our standard deviation is just confirming that numerically. So the standard deviation for McDonald's is greater than that of Wendy's, because the wait time for McDonald's has more dispersion. It's more spread out. Than Wendy's. Which we already knew by its graph, but this tells us that numerically. So something to note here is the closer the standard deviation is to 0, the less spread there is among the data. All right. So, standard deviation may be used to judge whether a particular observation is considered far away from the mean of a data set. So, for example, is 31 centimeters far away from 25? Well, it depends. If the standard deviation of the data set is 6, then the answer is no, because 31 would only be 1 standard deviation away from 25. However, if the standard deviation is 2 centimeters, then the answer is yes, 31 would be far away, because it would be 3 standard deviations from 25. So when judging the unusualness of an observation, it's vital that you consider the underlying variation in the data that's measured by the standard deviation. So a general rule here is 0 to 2 standard deviations away is typical or considered not far away. More than 2 standard deviations away is considered atypical or would be considered far away from the mean. All right, we're going to do an example with that here. So, is the number 1,000 far away from 900? As someone with knowledge of measures of dispersion, your answer should be depends, and it depends on what the standard deviation is. So, let's say the standard deviation is 25. Would we consider 1,000 to be far away from 100? Well, our mean is 900, our standard deviation is 25, and the value we are interested is 1,000. So I'm thinking, if I take the number 900, how many times do I have to add 25 to get to 1,000? Well, it would have to be 4 times. So that means that 900 plus 4 standard deviations is equal to 1,000. Based on what we just wrote, is that would be considered far away. Because the number 1,000 is 4 standard deviations away from the mean of 900. So now let's say that the standard deviation is 120. So our mean is 900, our standard deviation is now 120. We're interested in the number 1,000. So I'm thinking 900 plus what would get me to 1,000? And I'm thinking in terms of standard deviation here. So I'd have to add 100. However, 100 is less than 1 standard deviation. So therefore, 1,000 would be considered not far away from 100 because it's less than 1 standard deviation away from the mean. So it's actually really close. It's really close to the mean because it's less than 1 standard deviation. Whereas in this example, it was 4 standard deviations away from the mean. So it is far away from the mean. All right. Third here, we're going to determine the variance. The variance is just the standard deviation squared. So you have your population variance represented with sigma squared and your sample variance represented with s squared. So there's our data set. Compute the population and sample variance of this data. Well, for population, we know that sigma was equal to 11.36 minutes. So the variance is just sigma squared, which would be 11.36 squared, which is equal to 129.0496. And our units would be minutes squared. All right, your units get squared as well. Of that sample we took earlier, remember our sample was the numbers 5, 26, and 36. So S was 15.82 minutes. So S squared, which is the variance, would be 15.82 squared, which is 250.2724 minutes squared. All right, a lot of the times you're going to see the standard deviation referred to more than the variance, simply because in a lot of situations, variance doesn't make sense, because if you think about it, we're talking about minutes squared, and that just doesn't make a whole lot of sense here. So it's not really applicable to our specific data set, and I feel as if that happens a lot. So a lot of times we focus on the standard deviation to determine, where the data lies in comparison to the mean and if it's close or far away from the data. So last thing we're going to talk about here is the empirical rule, and this is this applies to a bell-shaped curve. So if it's bell-shaped, that means it's unimodal, so it has one mode, and it's also symmetrical. Okay, so what this empirical rule tells us is that approximately 68% of the data will lie within 1 standard deviation of the mean. Approximately 95% of the data will lie within 2 standard deviations of the mean. And approximately 99.7% of the data will lie within 3 standard deviations of the mean. So no, the notation they're using is with population, but it's the same thing. You can use this empirical rule with sample data as well. So instead of mu, you would use x bar, and instead of sigma, you would use s. This is sometimes referred to as the 68, 95, 99.7 rule. So those are three numbers that are important in this and that you need to know. So here is our bell-shaped curve. We're just going to draw the empirical rule graphically to help us kind of understand here. So in the middle of our data here, we have our mean. And then if we go to the right, 1 standard deviation, that would be the mean plus 1 standard deviation. If we go to the left of the mean, that would be that would be the mean minus 1 standard deviation. So then next would be our mean plus 2 standard deviations. Or to the left would be our mean minus 2 standard deviations. And then we have our mean plus 3 standard deviations and our mean minus 3 standard deviations. All right, so what the empirical rule says is that 68% of the data lies within 1 standard deviation. So 1 standard deviation below and above the mean. That's where 68% of the data will lie. 95% of the data will lie within 2 standard deviations. And then within 3 standard deviations, 99.7% of the data will lie within 3 standard deviations. So almost all of your data will lie within 3 standard deviations. 0.3% would lie outside of that. So with those 3 special numbers, we can then determine what percent of data lies within the mean and 1 positive standard or 1 standard deviation above the mean, or within 1 standard deviation below the mean. So if you take your 68% and split it in half, each of these parts hold 34% of the data. So then if I'm looking at this area here, to figure that out, I would take 95 minus 68. All right, so 95 minus 68 is 27. And so there's 27% between this light blue and this light blue. So if I cut that in half, 13.5% of the data would lie here, and 13.5% of the data would lie in the other part. So then to find this darker blue piece, I'm going to take 99.7 and subtract 95. And that's 4.7. If we cut that in half, that's 2.35. So 2.35% lies in this piece, and 2.35% lies in this piece. So then remember, your total area under the curve would add to 1, or 100%. So if you take 100 minus 99.7, you get 0.3. Divide that by 2. 0.15% would lie outside on the right, and 0.5% would lie outside on the left. So that is just a rule for where the percentage of data in your population or sample, if it is bell-shaped, how much of the data would lie within compared to the mean. So let's finish with an example. Using the empirical rule, the waist circumference of a 2-year-old male is bell-shaped with a mean of 48.5 centimeters and a standard deviation of 4.8 centimeters. Okay, if we're using the empirical rule, I would redraw this graph here, and then label it. So I'm just going to label mine with green. So I know the mean is 48.5. So then if I go one standard deviation above, I'm going to take 48.5 plus 4.8, which is 53.3. And I got that by taking 48.5 plus 4.8. If I add 4.8 again, I get 58.1, would be 2 standard deviations above. And then if I add that again, 3 standard deviations above would be 62.9 centimeters. If I take 48.5 and subtract 1 standard deviation, I get 43.7. If I subtract again, I would get 38.9, so that's 2 standard deviations below the mean. And then 34.1 would be 3 standard deviations below the mean. So about 95% of 2-year-old males will have a waist circumference between what values? So 95% of our data, which is our 2-year-old males, will be between 38.9 centimeters and 58.1 centimeters. What percentage of 2-year-old males have waist circumferences between 34.1 centimeters and 62.9? So 34.1 and 62.9, that's 3 standard deviations below and 3 standard deviations above. So that's going to be 99.7% of 2-year-old males. And then last, what percentage of 2-year-old males have waist circumference between 53.3 and 62.9? So 53.3 and 62.9. So this is where it's nice to know how to break it down into smaller pieces, because if I'm just finding these two, I'm just going to take the 13.5% plus the 2.35%. Which would give me 15.85% of the data would lie between those two values. All right. So you could find the actual percentage that lie between, but this is specifically using the empirical rule to estimate those percentages, which tend to be really close to the actual value if it is bell-shaped. Okay? And there you have measures of dispersion.